Good morning. Hope everyone is doing well. Today we're going to be talking about frequency response. We need frequency response for a variety of things. Since we're going to be talking next about filters, one of the key ways of defining what type of filter we have is this idea of frequency response. Now, I had mentioned this before, but let me go over it again. Sometimes the names that people give things are totally out there, and sometimes they're exactly the name they should be. And this is one of those cases. So we know that a linear time invariant system is defined, completely defined, by its impulse response, h of n. Now, and n, of course, is called the impulse response, as it should be. Now, if we take the Fourier transform of h of n, we get h of e of j omega, and that's what we call the frequency response. Okay, so a frequency response is basically the Fourier transform of the impulse response. As an aside, we know that if we take the z transform of the impulse response, we get what we call the transfer function. So let's start with the basic definition again. Suppose we have a linear time invariant system. X of n is going to be our input, h of n the impulse response, and y of n is going to be the output of the system. Now, a frequency response is very useful to us because it tells us how the system changes the input for different frequencies. It turns out that a linear time invariant system doesn't change all frequencies by the same amount. As we're going to see, what a linear time invariant system does, it changes the amplitude and changes the phase of the different input frequencies, but it never changes the frequency. So let's look at this and let's go through it specifically. So let's say that the input is a cosine. So we know three things define a cosine: its amplitude, its frequency, and its phase. In this case, right, the amplitude is A, the frequency is omega 0, and the phase is 0. It's easier if we write this using Euler's equation as complex exponentials. To calculate the output, we know that the output is just a convolution of the input with the impulse response, so it gets something like this. Substituting in this case what x is, writing it in terms of complex exponential functions, we get this. And then doing simplifications, we get this thing down here. Now, this term doesn't have k, right? Our summations are in k. This term has no k, this term has no k. So we're really looking at these two terms which have the summations. When we look at the first summation here, specifically, we see it's h of k e to the minus j omega 0k. This is exactly like a DTFT. The only thing is that instead of having a variable omega, we have a constant omega. And so this is, we could write it as h e to the j omega 0. The other one is going to be the same, except it doesn't have the negative, and so we need to put a negative here for the DTFT. And so this is the DTFT evaluated at omega 0. This would be the DTFT evaluated at minus omega 0. Now, to keep simplifying these equations, let's write the frequency response as magnitude and phase. And let's assume for the moment that h of n is real. In that case, right, writing h is the magnitude and phase. Now these two things are going to have the same magnitude, and they're going to have opposite phases, right? Because one is j omega 0 and the other is minus j omega 0. So we factor out the magnitudes, which are the same, and we leave the phases, which are different. And we can simplify this again to a cosine, and we finally end up with this final term here. And we compare this with what we had originally at the input, right? Our original input was a cosine with amplitude A, frequency omega 0, and we see that the output is also a cosine. with frequency omega 0. Now, what it means is linear systems, linear time invariant systems. If we give it a cosine as an input, it's going to be a cosine as an output, right? It doesn't change cosines into square waves or triangle waves or anything else. It's a cosine with the same frequency. The only thing the system does, it can change the amplitude and it can change the phase. How does it change the amplitude and how does it change the phase? Well, that's what the frequency response tells us. The magnitude of the amplitude, the magnitude of the frequency response tells us how it changes the amplitude. And the phase of the frequency response tells us how it changes the phase for these different cosines. Now let's look at this specifically for a couple of filters. So let's assume we have this h of n. We take its DTFT. So let's say that this is the impulse response of a system or of a filter. And let's calculate the frequency response of that system. So let's calculate the DTFT. So we just substitute in, we've calculated these things similarly before. Right, we're going to have three terms because there are only three impulses in h of n. And we can get this here. If we factor out e to the minus j omega, then we get something like this. And then these two terms, we see that they have the same exponents, except the difference in sign. So we can combine these two into 2.1 cosine of omega. So we end up with this term here, 0.6 plus 0.2 times cosine of omega. And we have e to the minus j omega factored out. Now this is nice. And of course now we can see why I factored out the e to the j omega. Because this term is always going to be real and positive. So this is our magnitude. And this is going to be our phase, right? And so we can get our magnitude and phase of the frequency response by inspection. Now let's look at the graph of the magnitude and the phase of the frequency response. The magnitude, if we were to graph the magnitude from 0 to 2 pi, let's start out 0, right, pi would be 3.14, this would be 2 pi here. So if we graph from 0 to 2 pi, we can see that, right, when omega is equal to 0, we have 6 plus 0.2, which would be 0.8. And then the smallest point is when cosine is negative 1, so it would be 0.6 minus 0.2, so it gets down to 0.4. And so this goes from a maximum magnitude of 0.8 down to a minimum magnitude of 0.4, and then back up. And of course we know this repeats. We're not going to keep graphing it out because we know that all DTFTs are periodic with a period of 2 pi. So if we graph it out for 2 pi, it's going to look the same to infinity. The phase is just a line, right? It's minus omega, so it's a nice linear function here. Now, what would happen if we give it cosines as input? Specifically, if the input is 3 cosine 0.2 n, in other words, it's a cosine with a magnitude of 3 and a frequency of 0.2 radians per sample. We know that the output is going to be this here. We know that the magnitude is going to change and the phase is going to change depending on our frequency response. And so we have to calculate these two numbers. The magnitude is this, so the magnitude evaluated at 0.2 is going to be almost 0.8, 0.796. The phase, since the phase is just a line, right, it's minus omega, the phase at 0.2 is going to be minus 0.2. Substituting that into the equations for omega, then we get this thing here. We see that the magnitude is going to be 2.39 and the phase is going to be 0.2. If we were to actually take a cosine and pass it through this system, this is what we would get. Right? Remember, the input has a magnitude of 3, and so we see that the magnitude goes up to 3. The output, as we just calculated here, is going to be 2.39. And we can see, right, we can verify visually that this is about 2.39. The output is also going to be delayed with respect to the input. How much of a delay? It's going to be 0.2 radians delayed. We could also look at this in frequency, right? A cosine is just a sequence of impulses. We did this in class when we did the DTFT of a cosine. So it's going to be impulses at the frequency, and we know they're going to repeat every 2 pi. And so these two impulses are going to repeat to infinity. So this would be the magnitude. Now, the magnitude of the filter, as we showed up above, is just going to look like a cosine oscillating up and down between 0.8 and 0.4. And so the output we know is going to be the multiplication of the magnitudes to get the magnitude of the output. Now what if we did this again, but this time for a cosine of frequency of 2 radians per sample? In other words, the frequency has changed, it's larger. In this case, the output is similar, except we have to calculate the magnitude and the phase at 2 radians per sample. If we do that, the magnitude at 2 radians per sample is about 0.5, and the phase is going to be -2. So substituting that in our equation for our output, again, the frequency of the output is going to be the same, but the magnitude and the phase have changed. The magnitude now is going to be about 1.55, about half what it was before, where we get that from the magnitude, right? The magnitude is about 0.5, so if the input is about 3, the output is going to be about 1.5. And the phase is going to be delayed by 2 radians per sample. If we actually look at this, we get something like this. Now, this is what MATLAB gives as an output. The signal, it doesn't really look like this. We know that discrete signals, right, only exist at the integers. MATLAB, you can tell it to graph it in different ways. In this case, I had it draw lines between the dots just so I could see which dots belong to which cosine. But this is not how the signal looks, right? Between 0 and 1, there's nothing. Between 1 and 2, there's nothing. And so these things that don't look much like cosines anymore, they're still cosines. Anyway, the input, we can see it goes up to 3 as it should. And the output, we can see it goes out to about 1.55. And again, why is it smaller than before? Well, the impulse of the cosines, instead of being at 0.2, are now out at 2. The magnitude is smaller there, so when we multiply 3 by 0.5, we get about 1.55. Now, in general, if h of n is the impulse response of a linear time invariant system, the output is going to be the convolution. Now, a convolution in time, you know, is a multiplication in frequency. And so if we look at this equation in frequency, this is what we get. Now, let's write each of these terms, y, h, and x. Let's write it in terms of its magnitude and its phase. So we'll write the magnitude and phase of y, magnitude and phase of h, and the magnitude and phase of x. Now, these, let's take and put the magnitudes together. And of course, these are exponentials, so we add the exponents to get them together. And now these two things, or the two sides of the equation, have to be the same. So the magnitude on the left side has to be equal to the magnitude on the right side. In other words, the magnitude of y has to be this multiplication, and the phases have to be the same too. So the phase of y is just the sum of the phase of h and of x. So in general, if we have any signal, let's say it's x of e to the j omega, and it has a maximum magnitude of a. And let's say this is our filter. We know that the output is going to be, or at least the magnitude of the output, is going to be the multiplication of these two terms. Now this goes to 0 abruptly at some frequency. So when we multiply them together, right between these two frequencies, the signal is going to pass through, multiplied by 2, in other words, it's going to get bigger. But outside of those frequencies, there's nothing going through the filter. And so we could think about this as a low-pass filter, where it lets frequencies close to 0 go by, but not frequencies close to pi. So let's look at another example. Instead of having the h of n we had before, let's look at this. Again, let's look at the frequency response, and let's graph some of the outputs. We have to take the DTFT as we did before. I'm not going to go through the whole procedure. I know you can do this. Pause the video, calculate what the DTFT is, and we get this thing here, right? We know that this has this transform, this, or by inspection almost, we can know what the transform is. And when we simplify it, we get this thing here. Now, in general, we might want to factor out e to the minus j omega. But let me write it like this, right? These two terms don't have the same magnitude, and so factoring this out is not the simplest way to go. But let me write it as real part and imaginary part, right? This complex exponential can be written as a cosine and sine. So this can be 0.1 cosine times j 0.1 sine. The same thing for the denominator, writing it as cosine and sine, we get this. Where this is our real term, this is our imaginary term. The same thing for the denominator. And I'm doing that so we can get the magnitude and the phase relatively easy. So how do we get the magnitude of this function here? Well, it's the same thing as we always do, right? When we have a complex number in rectangular form, it's the real part squared plus the imaginary part squared. We take the square root of that to get the magnitude. We do that for the numerator and the denominator, and that would be our magnitude of our system. How do we get the phase? Well, the same thing we do always, right? It'll be the phase of the numerator minus the phase of the denominator. And the phase of the numerator, right, is the inverse tangent of the imaginary part over the real part. And the same thing for the denominator. Now let's do the same thing we were doing before, and let's give it two cosines, or a cosine at two different frequencies, to see what will come out. Now we calculate the magnitude at each of these frequencies. We get 0.6 and more or less 1.9 for the magnitudes, and similarly for the phase, right? We can substitute here for the different frequencies and calculate what the magnitude and what the phase is, and this is what we would get. So in other words, our output cosines are going to be these two here. In this case, the input has a magnitude of 1 and a phase of 0. So the output is going to have a magnitude just 0.6 in one case and 1.8 in the other case. And these are the phases. Now let's look at the frequency response. If we were to graph the frequency response of this h of n that we had calculated before, it's going to be lower at low frequencies and higher at high frequencies. We also see that the phase is not the nice linear function we had before. Instead of being a straight line, we can see that it actually goes up and comes back down. Now, how do the input and output look for the different frequencies? For the frequency of 0.1 pi, so the amplitude of the input as before is going to be 1. The amplitude of the output is again 0.6 for 0.1 pi radians per sample is the input frequency. If we change the input frequency, we increase it. In this case, if we increase it to 0.87 pi radians per sample, the input is again going to be an amplitude of 1, but the output is actually going to be larger, as we would expect from the frequency response. So if we have 0.8 pi, this pi would be 3.8, so 0.8 is going to be around here, as we had calculated. The magnitude is going to be like 1.9, almost twice. So 1.89 should be the output here. And so we can see that basically it'll get up to about 1.89 is the magnitude of the output. So we have some homework problems. Do the homework problems in the syllabus. And I want you to repeat some of the stuff we did with these two filters here. Calculate the frequency response, sketch the magnitude and the phase. It doesn't have to be exact. I want to more or less sketch here for these two filters. Also, calculate the output of each of these filters for one specific frequency, in this case a cosine of amplitude 5 and a frequency of 0.2 pi radians per sample.